So you may remember in Math 243, if you took it recently at RCC at least, that you covered linear regression and calculating the linear regression line, or also known as the least squared regression model. So, and you may remember this equation right here, y hat equals b 1 x plus b0, and you calculated the linear regression using an equation, or depending on the teacher you had. I made my students do that because I like the math behind it. Some teachers just don't focus on that so much. But anyways, you would have at least calculated this and have seen this before. So this is, we're going to be dealing with that a little bit, but going more in depth and actually testing something involving the B1. As you know, the B1 and B0 are calculated based off of a sample. We're given a sample, and we want to figure out the best regression line that fits into this model. So we can still do that, and using the data set here, I'm going to be looking at problem 12, and we're going to be going into other sort of details of the regression line, and something that may look familiar from when you covered this, if you covered it in your Math 243 class. But we're going to be kind of going in a different route, more of a inferential statistics route and testing things. So problem 12 is on credit scores. So the credit scores are given, and the interest rate that were rewarded based off of a credit score are given for y. So x is your credit score, y is your interest rate that was given to you. And I inputted the values already into L1 and L2. And you can look in your book to see what those values are if you can't see it here. I'll zoom in a little bit so maybe you can see a little better. I don't know if that helps. Okay. Anyways, let's continue. All right. So we have these values in here, and part A of the problem is treating credit scores as the explanatory variable x to determine the estimates of B0 and B1, or not B0, beta0 and beta1. So beta0 is the population, represents population. The betas represent the population parameters of each of these. And we're trying to estimate what the population parameters are. We're trying to estimate what beta is. In this section, we're estimating what beta 1 is based off of our sample data. And the first step is just to determine what the estimates of beta 0 and beta 1. And the estimates are these two values right here. So we need to do our linear regression equation and figure out what that is. So we'll go stat edit. Oh. Let's go to stat calc linear regression. And you'll notice that we have A, which represents B1. So part A, we found that B1 is equal to negative 0.07637. That's just rounding to some decimals. And then we have beta 0, which is equal to 61.369. Okay, so there we go. We found the estimates of beta 1 and beta 0, and that's based off of the sample, the estimates, which is the best estimate of what they are, and that's based off the linear equation using those data values. And now the next step is actually somewhat time consuming and will take up most of our time. and that is to solve for beta 1. Or not beta 1, it's part B. It's to find S sub e, which is known as the standard error of the estimate. The standard error of the estimate is somewhat of a lengthy process, and it may be good to use Excel because it's set up kind of that way where you need to kind of use Excel to calculate the values. So first off, I'm going to use the calculator to do most of my work. And so the first step is to write out X and our Y values from our table. So we have 545, 595, 640, 675, 705, and 750. And our values are 18.9, our interest rate, that is 18.92, 17.967, 12.218. This is somewhat of a lengthy process, but this is something you actually should have done in your, or at least seen in Math 243, depending on your instructor. They would make you do this. But, so let's go ahead, continue, 6.68 and 5.15. All right, we know the interest rates go down as the credit score goes up. So that's what we would expect. There is some sort of relationship, and we would expect that to be a sort of a negative sort of slope, because as one goes up, one goes down. So that makes sense. Now that is these values right here are our actual Y values. Now we want to calculate what our Y hat values are, which is using this equation up here based off of these values. So I'm going to use my calculator to calculate each of these. And so let's go ahead and do that. And to quickly do that, we can go ahead and I need more light. Let's go over here. There we go. Okay, so I'm going to do the linear regression again. Second tree, linreg, and then I want to store that, so I would go to vars, yvars function. We want to store that into y1, and notice that those values are now in y1. Cool little trick if you didn't know. Table, and now I want to enter the certain values that I want in, so that's 545 would be the first one, and that would be 19.748. And then we want to do 595, and 595 gives us 15.929. And then we want to do 12.218. 12.218 is 60.436. Oh, what am I doing? Sorry, that is wrong. I have to plug in 640, not 12.218. 640. I'm just going to plug them all in. 675, 705, and 750. So I could just read them off. All right, so I have the values 12.492. And then we have 9.8196. Or 9.8196. 7.5285, and then 4.0919. All right. So there's our white hat values, and as you can see, as you can imagine, these are our actual values, and this is based off of what fits the best. And we want to figure out, is this really accurate compared to this? And as you can see, we can see how far they deviate from what they should actually be. Okay. And so naturally we would want to do y minus y hat. So we want to do y minus y hat, and I'm going to do it all in one step, and then we square it because we want to sort of just find the standard deviations of each of our errors. So let's go ahead and do that. So let's get out of there. 18.982 minus 19.748 is negative 0.766. Oh, and then square it, sorry. So I'll just say square, and then the rest of them will actually square. 17.967 minus 15.929, 4.1534, and then we have 12.218 minus 12.492 square. That would be 0. That's pretty good. We like those. And then we have 8.612 minus 9.8196. Square that. 1.458, say 3. And we have 6.68 minus 7.5285. Square that. 0.71, or pretty much 2 actually. 5.15 minus 4.0919. Square that. We get 1.12. All right. And then our next thing that we would want to just put right here. Next thing we want to do is sum up all of our square residuals. So this is a residual in here, right in there. That's the residual y minus y hat. And then we want to square them. So that's the sum of your square residuals that I'm about to calculate. And so negative 0.766 squared plus 4.1534 plus 0.075076 1.4583 plus 0.72 plus 1.12 is the following. That would be 8.114. All right. Now the last step to find S sub E is to take that the sum of the square residuals 114, and divide that by n minus 2. So as we can, dividing by n minus 2, since there's 1, 2, 3, 4, 5, 6 different values, we would just divide by 4 and then take the square root of that. Okay, so let's go ahead and do that. Second square root. 4 is 1.424. Let's say 1.42. And I rounded a lot of things, so chances are I'm a little off. According to the answer here, I'm right. Wow, that's convenient. Actually, really close. Okay, so that is 1.42, the standard error of the estimates. So now our next step, that's part B. Part C, I'm actually going to do on the next page. Part C is solve for S sub B1. So that's the standard error of our B1. And the standard error of our B1 is used by or is calculated by using the following equation. Is the standard error of our estimates divided by the square root of n minus 1 times S sub x. So we want to find our standard error of our x values. And the standard error of our x values is quite simply just find the standard deviation of x. So let's go ahead and do that. And how we can do that is we just take our x values. Notice our x values are in L1. So we just want to do delete stat calc 1var stats on L1, and so that would be S sub x. That would be our standard deviation of our x values. Sample standard deviation, of course. So taking our S sub b, what was our S sub e? I mean, our S sub e from the previous page, 1.42, and divide by that by the square root of n minus 1. So that is the square root of 5, because n is 6. And then we multiply that by 74.54. So our S sub b, or our standard error of our b, is the following: 1.42 divide the square root of 5, 74.54, and we get the value 0.00852. 852. And just checking the solution. Yep, that's the right answer. Okay, so just to kind of think of what's going on here, we're finding the standard error of beta sub 1. And I mean, I similarly to how we proved in week 5 prompt 1, the week 5 class discussion prompt 1, we can use a similar sort of idea of proving that the standard error of beta 1, which is slope, is the standard error, which is the standard error of our y values divided by the standard error of our x values. Because if you think, slope is equal to, if you just think in general, the change of y over the change of x. Similarly, the standard error of the slope, beta sub 1, or b sub 1, is equal to the standard error, very similarly to the standard error of y over the standard error of x. So that kind of makes sense that that would be our standard error. So that's 0.00852. Okay, so that is part C of the problem. Let's go ahead and go into part D. Part D is test whether a linear relationship exists between credit score and interest rate as at the alpha equals 0.05 level of significance. So we've done pretty much all the work we needed to with parts A through C. Parts A through C is just taking you step by step in order to find our standard error of beta sub 1. So we are pretty close to finding our test statistic, because we know that the test statistic is for okay, well, I should mention this, that if we're testing if there's a linear relationship, we're testing something about beta sub 1. And so let's just go through the steps of the hypothesis test, which they outline in this section 14.1, or equivalently 7.1 on the custom edition. Yeah, 7.1 of the custom edition. So we have some preliminary requirements: that the sample is obtained using a random sampling, like always, and the residuals are normally distributed with constant error variance. So I haven't really explained that that requirement for for this section, but they talk about that in the book, that the residuals are normally distributed with constant error variance. And the constant error variance is actually sigma squared. So here's just a picture in where you should be looking in regards to that step. And they talk about it here. I'll just show you really quickly. This part of your book, they talk about the requirement 2 right up here for the inference on least squared regression model, that the response variable is normally distributed and has a standard variance. And this is kind of the picture of it. If you find the linear regression line, and then here's the dots, you can kind of imagine a scatter plot, and then the best fit line, the lin reg line, going through. And what they're showing is that it's normally distributed for each value of x, which is kind of weird and hard to picture. But and that the standard deviation of this normal distribution for all values of x is equal throughout. So notice that the normal curve is equally wide throughout, and they're normally distributed. Testing this, you will be dealing with the normal probability plot, which looks something like this. And the idea, you'll be given a homework assignment. If there are any red dots that are beyond the outside curves, which we'll be dealing with more in the next section, this is called a confidence band. Anyways, if there's any of your data points outside of this curve right here, then it is not normally distributed, your data values for each value of x. So in my previous class, we actually built these and constructed them using Excel. I'm not going to make you do that. StatCrunch might actually do it. I haven't looked into it, but it's not that big a deal. Most homework problems, it'll give you something like this, and you just have to notice, are there any dots that are outside of these two outside curves? And you'll just notice yeah or no, and that will tell you if it's normally distributed. And then let's see if I can find it. Here you go. This is the test for standard deviation, equal standard deviation throughout. And as you can see, you'll see pictures like this where it'll be residuals versus the x. A bigger picture. Well, anyways, you'll see something similar to this on your homework possibly, and you should be able to tell based off the spread. Are they kind of spread out evenly throughout? Like, you don't want it spread out really wide here and then have them just kind of get more narrow throughout. Then that's not an equal standard deviation throughout. You want them to be spread out equally throughout. That tells you that they're equally standard. There's an equal standard deviation throughout for each value of x. And it's just an observed thing. You look at a graph and you tell. And so when you're checking the two requirements for this hypothesis test, well, actually the number 2 requirement, which is residuals are normally distributed with constant area variance, you'll if you're going to be testing that on the homework, they'll give you the pictures. You just have to observe them and say, yeah, they look like they are. We have step 2 met. So you'll see that in the homework. Anyways, so those are the first 2 steps. And step 1, I'm just going to go through each of the steps. Step 1 is a null and alternative. And the null is always, since we're testing something based off of either, we're testing something about beta sub 1, the slope. And that is you always put the population parameter in there, and that's beta sub 1. And is that equal to 0? Always equal in the null, as you know. And so equal to 0, that's saying that there is no relationship. When the slope is equal to 0, that means there's no relationship between your x and y. So that's what the null is saying, that there is no relationship. And h sub 1, it could be a 2-tail, 1-tail, either left or right tail test, saying like, is there a negative or positive or any relationship based off the wording. So in part D it says test whether a linear relationship exists. So we're just testing to see if there's one that exists. So in that case, it's a 2-tail test. Beta 1 is not equal to 0, saying that it could be a negative or positive. We just want to know, is there a relationship between the 2 variables? That's saying that the slope is non-zero. So let's go ahead and test that. So step 2, so there's step 1. We've already done the preliminary requirements. We're assuming that they're correct at this point. Step 2 is just quite simply state your alpha. Okay, good. Step 3. Step 3 is compute the test statistic, and we've done a lot of the work already for that, which is calculating S sub B sub 1. And that is equal to B1 minus beta 1 over, so we're testing our our point estimate of beta sub 1, which is B sub 1, our best estimate of what this is, minus B sub 1, or beta sub 1, and that is always 0, which is kind of convenient. And then we are dividing by the standard error of beta 1. We always want to divide by the standard error of whatever this variable is. Okay, so that is why we just calculated the standard error B sub 1, is because we're testing something based off of beta 1, and our estimate is B sub 1. So there we go. We've done a lot of the work, and we notice that we have all the information needed. So this is just quite simply B1 divided by S sub B sub 1. And we know that that's 0.00852. And we know that beta sub 1 we calculated back here is this value right here, negative 0.07637. So based off the wording, it's a 2-tail test, but obviously between a left or right tail test, this would be a left tail test. That and the left tail test is stating that the alternative is stating that there is a negative relationship between the 2 variables, which means you have a negative slope. But anyways, we're doing a 2-tail test based off the wording. Let's go ahead and calculate that. That's negative 8.96. Negative 8.96 is their test statistic. Now, as for a critical value, now remember that we divided by n minus 2 back here. That was n minus 2. And the reason we divide by n minus 2, that's our degrees of freedom. Our degrees of freedom this time is n minus 2. And the reason we're subtracting 2 is because we have two unknowns. It's all because of this. B1 and B sub naught are unknowns. Since we have two unknowns, like then we our degrees of freedom is defined as n minus 2. So we'll be using that for the critical value. So our df equals 4, and our alpha equals 0.05, and we would be looking up on the t-table what our test statistic would be, and 0.05, degrees of freedom 4, we have 2, with the two-tail test, watch out, since it's a two-tail test, we actually need to look up alpha divide 2 equals 0.025. It's a two-tail test. We got to split up the tails into two equal sections. So I'm actually looking up this. 2.776. So just to see a picture, we have so t sub alpha over 2 is equal to 2.776. Looking up on our t-table. So negative 2.776 and 2.776. And notice that value right there, our test statistic, is way the heck over here. That is totally in the rejection region. And that's essentially telling us that we're rejecting H naught, of course. So that's saying that there is a linear relationship between X and Y. That your credit score does have a strong relationship, and it's actually a negative relationship if you kind of think about it. It's a negative relationship between compared to your credit score. As your credit score, or as your as your credit score goes up, your interest rate will go down for whatever loan you apply for. So that's what we've just determined with rejecting H naught, rejecting that there's no relationship. So stating your conclusion, look up on your flow chart, that's step 5, and notice that I'll just start it out, step 5, if you don't understand it yet. Step 5 is you would state, you'd figure out if the claim contains equality, and that is saying, well, let's see here. Test whether a linear relationship exists between the credit score and interest rate. Linear relationship is actually not equality, because it's all based off of B1, and equality is saying that there's no relationship. That's what equality means in this case. So it's kind of weird. So there is a relationship is saying that beta 1 is not equal to 0. So the answer would be no, because they're saying is there a relationship? So no, it does not contain equality. And then step 2 of the flow chart, did we reject H naught? Yes, we did reject H naught. And that would tell you your wording. We would be on option 1. Yes. So we would be on option 3. Okay, so we're in option 3. So you'd state the words in option 3 of the flow chart, and you'd state it, and you would just copy and paste the fact. You would say there is a linear relationship that exists between the credit score and the interest rate at the alpha equals 0.05 level of significance at the ... Okay, so there we go. This is somewhat of a process in a way, but hopefully you can kind of realize why we're looking at slope if we're trying to determine if there's a relationship, and why no relationship means that the slope is 0. If you can kind of imagine, I'll just draw a picture. If we were to plot a bunch of values that have no relationship, you'd expect them to just be random dots all over the place. And when you do a linear regression line, you'd expect it to be flat. If it's just a horrible relationship between x and y, you'd expect the linear regression line to be flat. So that's essentially saying beta naught, our slope, is equal to 0. And just because your b sub, or not b, beta sub 1, sorry, and just because your b sub 1, your estimate, is really close to 0, like our estimate back here, notice that our estimate is really small. That doesn't mean that there's no relation, that it's like it's going to have a really bad relationship. It just kind of just tells you that there's a slope I mean, we're comparing x values that are, you know, really large compared to y values that are really small, because we're comparing credit score to interest rate. So you would expect the slope to be really close to 0, because y divided by x, the change of y over change of x, is slope, and that's a really small value. So just because this is close to 0 doesn't mean that it's bad. It doesn't mean that at all. A lot of people get confused with that. So, and again, you can do a test on StatCrunch like I showed you on the 13.1 extra video there. So I'll have you read up on that, but I'm going to go at the end of the section 14.1 after the stuff here. And under StatCrunch, it says that you can select stat, regression, simple linear, and it will allow you to do the hypothesis test of a slope. And you can also do a confidence interval for slope. I did not do that here, but you can do a confidence interval for slope on StatCrunch. Every section where you have every section that we've really covered should have a thing to do on StatCrunch to solve certain problems. But it does suck, but you have to have actual data values, not like statistics. You have to have the raw data values to be able to do something on StatCrunch, which is unfortunate. Anyways, let me know if you have any questions. That's kind of a quick look. Took 40 minutes, but of section 14.1. And there's one remaining video for chapter 14 on 14.2, covering confidence intervals and prediction intervals, which I'll cover next. Okay? Let me know if you have any questions. Bye.